Welcome to the Briefs lesson on turning. This lesson is part of a series that teach you the basic maneuvers you need to fly an airplane. We'll start with some revision from our previous lesson on climbing and descending. Can you explain the relationship between the four forces in a climb? State the definitions of best rate of climb and best angle of climb. What is the best range glide speed for your type of airplane? Can a glide distance be stretched? If so, how? In this briefing, we are going to learn how to enter and maintain medium-level turns, climbing turns, and descending turns. Then, how to exit the turn onto a given reference point. Our outcomes for today are: explain why rudder is required to maintain balance during a turn. Explain why back pressure is applied to the controls when turning. Given a particular turning scenario, state whether there is an over or under banking tendency, explain why, and describe pilot actions to maintain the nominated bank angle. Given a picture of a standard instrument panel, describe a typical visual scan during the turn. Given an indicated airspeed, state the angle of bank required to maintain a rate 1 turn performance. What is the definition of a turn in the context we are using it? A turn is a maneuver where the aircraft changes heading at a constant rate, whilst maintaining, gaining, or losing height, while in a state of balance. In level flight, as you now know, the forces are in equilibrium. These forces are required to remain in equilibrium during the turn. Let's take a 30-degree turn. It's a standard bank angle for a visual flight. You'll be doing plenty of these throughout your training. When we roll into the turn, the vertical component of lift, shown in green, tilts towards the direction of the turn. This causes the lift to have a horizontal component, which is no longer pointing straight upwards. The horizontal component provides the turning force. This is called centripetal force. It means moving, or tending to move, towards a center. You could imagine a string coming up from the top of the airplane in the direction of the green arrow. If you were to spin the airplane on that string, you are doing exactly what happens in a turn. As the horizontal component of lift is reduced, because it is now pulling into the turn, there is not enough lift to maintain level altitude. An increase in lift, either through angle of attack or increased speed, is needed. The usual way to manage this is through increasing the back pressure in a turn. So, the greater the angle of bank, the greater the angle of attack required to maintain a level turn. Once you get to 45-degree turns, a power increase is needed. But that's for another lesson. By increasing the bank angle, the angle of attack is required to be increased to maintain level flight. This greater total force creates a greater turning force, and a tighter and faster turn is created. This centripetal force creates a greater load factor. A load factor is the ratio between the lift and the weight of an aircraft. So when lift is increased in the turn, the weight is increased. This puts extra stresses on the airframe and the pilot. The engineers will take that into account when designing an airplane. There are different types of turns available, depending on the circumstances in flight. When learning to fly, and when flying under visual conditions, that is, when you can see out the window and use the horizon for guidance, turns are made at 30 degrees angle of bank. That is called a standard rate turn. When flying in instrument conditions, when visibility outside the airplane is not possible, turns are done at what is called rate 1. The definition of rate 1 is a turn maneuver in which an aircraft changes its direction at a rate of 3 degrees per second. This equates to 360 degrees, a full circle, in 2 minutes, for light and medium-speed aircraft. For high-speed aircraft, the standard rate of turn is 1.5 degrees per second. That equates to 360 degrees in 4 minutes. We will now look at how to determine how the turn will be rate 1. A rate 1 turn will be used for climbing turns, and, as mentioned, it is used for instrument flying. It provides a lower bank angle, which creates less movement for the pilot and less disorientation when flying under instrument conditions. It also enables air traffic control to know how long a turn will take, helping them to plan accordingly. Here's a shout out to our helpful friends in air traffic control. To determine the rate 1 turn angle of bank, simply find 15% of the current airspeed. So if you are flying at 100 knots, it will equal 15 degrees of bank. Let's look at some other ways to find the bank angle for rate 1 turns. Flying at 80 knots. Drop the 0, which leaves 8. Half of 8 is 4. So add the 4 to the 8, and that gives us 12 degrees. So a rate 1 turn at 80 knots will equate to 12 degrees of bank angle. What about when we are flying at over 100 knots? The same method can be used. Let's take 120 knots. Drop the 0. That's 12. Half of 12 is 6. Add 6 to 12, and our bank angle for 120 knots is 18 degrees. You may have now realized why there is a 4-minute turn for high-speed airplanes. Take 200 knots. Drop the 0 to get 20. Half of 20 is 10. Add 10 to 20 is 30. So that's already a 30-degree angle of bank. It makes sense to limit the bank angle at these speeds and not have airplanes flying excessive bank angles. Usually, 25 degrees is the maximum bank angle in controlled airspace. Depending on the type of instruments you use, the rate 1 turn will be depicted differently. For a newer glass-type instrument panel, the rate 1 turn will be indicated by something similar to the Garmin 1000 shown here. On the Garmin, there is a magenta line above the heading rows. You can see to the left of the current heading, 2 lines. The first indicates a rate 2 turn. That takes 4 minutes to complete a 360-degree turn. The second line indicates the rate 1 turn. You can see the rate 1 turn indicated here. On the analog instruments, a rate 1 turn is usually indicated on a turn coordinator as shown here. When the airplane symbol's wings are on this line, the airplane will be achieving a rate 1 turn. Be aware, this is the only thing it represents. It shows a rate of turn. It does not show bank angle. You can see here that when achieving a rate 1 turn, all of these airplanes will be completing a 360-degree turn in exactly 2 minutes. So the rule is, if an airplane traveling at a given speed uses 15% of the airspeed to determine the bank angle, it will achieve a rate 1 turn. If all turns are at rate 1, they are completed in the same time. When turning at rate 1, the diameter of the turn is approximately 1% of the indicated airspeed. So, at 150 knots, the diameter of the turn will be around 1.5 nautical miles. We have looked at rudder in previous lessons. You will be aware now that the rudder is used due to the secondary effect of ailerons, which is adverse yaw. Whenever we create more lift, we will always create more drag. This is an unshakable law. So the aileron, which moves downward, creates more camber, which creates more lift, which in turn creates more drag. Nothing new there. This results in a yaw away from the direction of the intended turn. There is a great coordination exercise you can do in a simulator or in your airplane. It really shows the art of using the correct amount of rudder input for a corresponding aileron deflection. If a large aileron input is applied, a large amount of rudder is applied to oppose the increased aileron drag. A small aileron input only requires small rudder pressure due to reduced aileron drag. So, when flying, you take a point in the distance, keep flying towards it, and slowly bank to the left, up to 30 degrees. As you near 30 degrees, stop the roll, and start the roll to the right. You will really be tested when you change direction of the roll. Keep balanced. Keep this going to the right. Then back to the left, and on and on. It definitely takes a bit of practice to get it smooth, but can make your rudder usage very smooth indeed. As part of airmanship and safety, you will be shown to always look out before commencing a turn. The basic considerations for this is that before commencing a turn, always clear the surrounding area first. Clear the airspace in segments, allowing your peripheral vision to detect movement. A good rule is to clear into the turn. So in this example, we are turning to the left. First, look to your right and clear the area. Scan to the center of the windshield and clear in front. Scan to the left wing, into the direction of the turn, and clear the area. Scan to the area behind and to the left, and clear the area. As you do this, stop the scan every 30 to 45 degrees and focus on something around the horizon. By focusing on something stationary, you will pick up moving objects quickly. How to turn an airplane. The basic procedure is this. Look out, as just discussed. Aileron and rudder, balanced and coordinated into the direction of the turn. Add back pressure. This is due to the reason we discussed at the start. Due to the lift acting into the turn, there is less available to maintain level flight. So added back pressure will compensate for that, by adding lift. Once established in the turn, the controls can mostly be centralized, and the airplane will maintain the turn, with your help. When turning, one wing travels further than the other. Therefore, faster and creating more lift than the other. This makes the wing want to overbank. You can see here that the left wing is traveling a further distance. As it's traveling further, it's passing through more air, and that creates more lift. So the left wing will want to increase its bank angle. This is why you want to centralize the controls, and then maintain the bank angle, with small inputs as needed. Let's take a climbing turn. We can graph this to make it easier to visualize. In a left climbing turn, the outer wing travels a greater distance, due to the direction of the turn. This creates more lift in that wing. But then there's another factor. The outer wing is also assuming a larger angle of attack, due to the fact it is gaining more height than the inboard wing. This again creates more lift. So in a level turn, and in a climbing turn, the airplane will want to overbank. It will want to bank more than you ask it to. When descending, the inner wing now has a larger angle of attack than the outer wing. This makes the wing want to underbank. Let's graph this again. The inner wing, due to the greater loss in height being experienced, will have a larger angle of attack. As the inner wing creates more lift, it wants to rise more than the outboard wing, and so tries to flatten the bank angle. Here's some more information on balancing a turn, and why it's so important. In a coordinated turn, the balance ball is centered and the airplane experiences a balanced turn. The occupants don't feel the turn. You can see online videos of people doing barrel rolls and other maneuvers which are balanced, and they can pour a glass of water while upside down. Don't try that at home. We know that rudder into the turn is required. In a right-hand turn, right rudder is required. The balance ball is set up to be stepped on. That is to say, that if the ball is to the left of center, as in this example, more left rudder is required, to assume balanced flight. So in this example, there is too much rudder being applied. It's similar to skidding around a corner in a car. There's just too much centrifugal force. So we say, the airplane is skidding into the turn. In this example, the balance ball is out to the right of center. So more right rudder is required. Remember, step on the ball. The nose of the airplane is facing away from the direction of the turn. So, it's said to be slipping away from the turn. The only correction needed in these examples is more or less rudder applied. Here is the scan cycle for entering a turn. Set power. Depending on the angle of bank, and whether it's a climbing or descending turn, you may, or may not, require additional power. Generally, a level turn, up to and including a 30-degree angle of bank, does not require additional power. Roll into the turn with coordinated aileron and rudder, to set your angle of bank. Keep the balance ball centered throughout. As the bank angle goes through around 15 degrees, add 1 to 2 degrees of increased pitch. This increases the lift and stops from descending. The amount needed will greatly depend on the type of airplane you are flying and other factors. Remember to never try this without a qualified instructor and in accordance with your airplane and company procedures. Once stabilized, check the level performance. The altimeter and VSI should both remain static, with no change. Remember, the vertical speed indicator is a few seconds behind the changes you've made. So always use an attitude to set up and hold the pitch attitude. Once stable, check it. Adjust back pressure if required. Let's say you set up into the turn and notice a 500 feet per minute descent. Look back outside at the attitude. Raise the nose a degree or two. Hold it. Wait 2 to 3 seconds and check the altimeter and vertical speed again. If, for example, you see 250 feet per minute descent, you have fixed the problem. Look at the attitude outside again, and then raise the nose a similar amount. It's important to look at the attitude when adjusting it and not the performance. This will stop you from chasing the instruments and flying really, really badly. Sorry, but it's true. Now, once you get the level turn going nicely, you know what the attitude is. Copy that picture into your mind. Because that's going to be the attitude you always use for that turn. It doesn't change. So once you know it, you don't have to learn it again. Then, monitor for the rollout point to end the turn. Keep cycling through these steps. Here is how to anticipate when to end the turn. A rule of thumb is, start the rollout at 1/3 of the angle of bank, before the desired heading. So, for a 30-degree angle of bank turn, start a rollout 10 degrees before the reference point or your desired heading. Roll out of the turn using aileron and rudder together, to keep balanced. When approaching wings level, centralize the controls, and release back pressure. It takes some practice, but soon you'll be able to turn out and stop where you want to. That's really all there is to exiting the turn. In summary, we have looked at forces in turns, types of turns, including rate and radius of turns, coordination, and its importance in being a proficient pilot, entering and maintaining a turn, and recovery to straight and level, over and under banking tendencies in turns, balancing in turns, and maintaining a turn, and visual scanning. Our outcomes for today are: explain why rudder is required to maintain balance during a turn. Explain why back pressure is applied to the controls when turning. Given a particular turning scenario, state whether there is an over or under banking tendency, explain why, and describe pilot actions to maintain the nominated bank angle. Given a picture of a standard instrument panel, describe a typical visual scan during the turn. Given an indicated airspeed, state the angle of bank required to maintain a rate 1 turn performance.